Okay, so let's start with the practice. We're going to be using different R packages to practice supervector machines and neural networks. Let's start with supervector machines. So for this exercise, we're going to be focusing on one classification task, which is basically automatically identify characters from the English alphabet written by hand. We're going to be using a data set that has 20,000 samples of capital letters. And some are written, some are just randomly reshaped and distorted. And so what we're going to do is use part of that data set to train a supervector machine to identify letters, and then we will test how well the supervector machine is working. Each letter is represented by a set of pixels, and so you will see that we have 16 different variables that characterize a given letter. And so, the supervector machine that we are going to be training is going to use these 16 distinct features to be able to identify different characters. So, we're going to be reading the CSV file, which is called letterdata.csv, and we'll check it a little bit. So let's start with that. I'm going to move this here, and we can start with R. Okay, so the first thing that we're going to be doing is read our data set. Read the CSV file, which is called letterdata.csv. Okay, we can now view this file. As you can see here, we have 20,000 rows in here, okay? And then you can see that these are all the different features that I was talking about, basically characterizing, the 16 pixels that we have. And these, as you can see, are, all the different 16 different features that characterize the distribution of pixels, okay? Okay. So, as you will see, let me open this as well. So if we check, the list of variables or features that we will use for the prediction, you can see here that letter has been loaded as a character. This is interesting. For some R versions, this is loaded as a factor automatically. For others, it's not. So if that's the case for your specific R version, you will need to transform that letter as a factor, okay, so that we are able to actually do classification tasks on them. So, we take the letters data frame and specifically the letter column and transform that as a factor. Okay, and so if we now check letters again, you will see here that now letter is a factor and that it has 26 levels, meaning that there's different 26 letters to choose from. Okay, so the next thing that we do as usual, we are going to be dividing the data set into training and testing. So we take the letters data set and create a training data by basically using the first 16,000 lines. And then we create the testing data set by using the remaining 4,000 lines and all the columns, okay? We can, again, just to make sure that everything is right, we can check the training and the testing data sets. This is a training data set with 17 columns, the letter plus 16 features and 16,000 entries. And we have here the same thing for the testing data set with the 4,000 entries, okay? Okay, so now that we have our training and testing data sets, there's different packages in R that allow you to run a support vector machine. Okay, I list there some. You are free to go and use whichever you prefer, or if you want to play around with different packages, go ahead and do that. Specifically, we're going to be using this library called kernel lab. So, I'm gonna upload it. Remember that if you have not installed this package, you will first need to install package kernel and then to basically load the library. And so, the function that we need to use to train an SVM from using kernel is called KSVM. Okay, and so KSVM, we need to input what's the variable that we are trying to predict. In our case, we are trying to predict the letter. We need to specify what's the training data set, and we need to specify the type of kernel that we'll use. Let's go ahead. KSVM, we want to predict the letter, and we're going to be using all the variables to predict it, the 16 different columns. The training data is going to be letters train, and then the kernel that we will use, we are using a vanilla dot. And I will explain you in a second what vanilla dot is. Now you'll see that in today's class, some of the commands that we'll run for training and testing, especially for the neural networks, might take a little bit longer, okay, because it's sort of more complex models that we are training. But if we look at the classifier, let me open this larger, you will see that, this is basically the support vector machine that has been trained to predict the letter using the 16 different features. And we see a couple of interesting pieces of information here. The vanilla dot is just a linear kernel function. Okay, remember when we were talking about data points being linearly separable or not, or whether we need to project the features to a different space. Here we're using the simple support vector machine approach, which is just, like finding this sort of linear approach or hyperplanes that will separate the samples as they are. No need to project them to another space. And then the second interesting function or piece of information that we find here is the number of support vectors. It's 7,000. So out of all the training data points that we have, 7,000 of them are the ones that we are using to find that hyperplane that separates the different samples. In this case, remember that this is a multi-class setting for a support vector machine, okay? And the package itself is gonna find hyperplanes that divide the different conditions for the different letters. And so that's highly probably that's the reason why we were using so many support vectors, because we are finding different hyperplanes to identify the different letters that we have. Okay. Okay, so now we have trained the model, okay? Of course, we want to see how good the model is. So now we're going to be using our testing data set to see how well we can predict what letter we have, okay? And so to do that, we're going to use the predict package. So, I'm going to save all the predictions in letter predictions, and I'm going to use the predict package. I'm going to specify that I want to use the classifier that I just built, okay? And that the testing set is going to be letters test. Okay, so if you take a look at the letter predictions, at the head, what you see here is just a few letters, okay? In fact, if you take a look at the whole data frame, what you see here basically is that for each of the testing samples that we have, the 4,000 testing samples that we have, you have a letter assigned to it. These are the letters that have been predicted, okay? So in our testing data set, for each set of 16 features that we have a ground truth, and then these are the values that have been predicted, okay? So because this is a classification setting, right? It could be to be able to understand how good this classifier is. One thing that we can do is basically look at the confusion matrix, right? Although in this case, because it's a multi-class problem, it has a lot of information, but the first thing that we can do is look at the confusion matrix. Remember that the confusion matrix is going to tell us for, basically each of the classes that we have, how many were correctly predicted and how many were wrongly predicted. So in order to compute, the confusion matrix in this setting, we can use the table command. And we basically want to compare, the predictions from our vanilla dot super vector machine and basically the actual or the ground truth values that we have in our testing. This outputs these really large tables that you also have in the slide, right? And this is nothing else. If you look at these columns, these are the letters that we predict, right? And the rows are sort of the ground truth values that we have. So to give you an example, for example, whenever we predict the letter Z, right? The letter Z, basically 132 times the letter was correctly predicted. This is good. But there were some instances where, we predicted an S when it was a Z 18 times. We predicted a T when it was a Z 3 times, right? And similarly, if you scroll up, when it was a Z, sometimes there were some A predictions, D predictions, and I predictions, and J predictions. Okay, those are kind of less expected. But this is the way you can interpret this confusion matrix. It's not as manageable as the smaller confusion matrices that we've used. And so, another suggestion that I had in order to understand or evaluate, accuracy of the model is to basically count how many times the letters were correctly predicted, right? And so what I'm doing here is that I'm creating a new variable that I'm going to call agreement. And agreement, what I'm going to be doing is just basically looking at the letter predictions that we have, okay? And I'm going to say, okay, how many times these letter predictions are actually similar to the ground truth that we have in the testing data set, okay? So if we do that, we are literally counting exactly what I just showed, like how many times the letter Z was actually, a value in the testing data set that was correctly predicted. And then we can show a table for this. We can represent this in a table format, okay? And this is going to tell us, okay, so out of the 4,000 samples that we had for the testing, 3,357 times the letters were the same letters that the ground truth that you had in your data set, okay? And 643 times they were not. And the prop table is just another way of computing these things. So you could also, rather than show full counts, you could also look at proportions, okay? Which is, 83 or almost 84% of the times we correctly, or the supervector machine correctly predicted the letter to be the expected letter. 16% of the times did not. Okay, this is a pretty good classifier actually. For a simple, vanilla dot linear supervector machine. And so the next thing that we want to try, of course, is what happens, as we said, when we were covering the theory for supervector machines, is that oftentimes the literature has reported that radial basis function generally outputs better performances than more simpler linear approaches to supervector machines, right? So, it's not about assumption to assume that the samples might not be linearly separable, and that then projecting those samples to a different space and trying to find the hyperplane in that different space might be easier or might actually improve, the classification or the regression results of the supervector machine. And so what we want to do here now is to basically use a supervector machine trained with a different type of kernel, with a radial basis function kernel, and see if by projecting the samples to a different space, we actually improve the accuracy of the classification, okay, as many other papers have shown before. And so I'm going to create a letter classifier RBF, where I'm going to save my trained model. I'm going to train the model with letter. That's the variable that I want to predict using all of the features. I'm going to be using the letters train data set, and then the kernel, rather than using a linear kernel or a vanilla dot, we're going to be using a radial basis function kernel. Okay. And so we train this model. Once the model is trained, we will use the predict function to exactly do the same process that we did with the vanilla dot. Sometimes these processes, again, take a while. Why is this taking longer than the vanilla dot? Well, because here again, what we are doing is that we are taking all the training data, or training data set, we are projecting the samples to a different space. And then, you know, what the package is doing is that it's trying to find that hyperplane that separates everything in a different space, in a projected space. And so that usually, you know, takes longer because that's much more computations that, you know, the package needs to do. And so now I'm going to save the predictions that I get using the predict package. Okay. In this case, I'm going to use the classifier that I have just created with the radial basis function and the same testing set. Okay, and you know, similarly to what we did with the linear vanilla dot, we can also compute the agreement. Okay, so what we're going to be doing is that we're going to be computing the agreement for the RBF, and the way I'm going to define this is by just looking at how many times the predictions from the RBF were the same as the ground truth that we have in the testing data set, specifically in the letter column. Okay, and then we can compute the table for this agreement. What do we see? What we see is that, you know, the number of true cases. Let me look for the table agreement for the prior case. So basically the top numbers are the agreement for the radial basis function. The bottom numbers are the agreement for the linear, the simpler vanilla dot kernel, right? What do we see? We see that using a radial basis function as a kernel has improved the number of cases where the letters have been correctly classified for around like 400, more or less 400 cases. So 400 additional letters have been correctly classified by using a radial basis function kernel instead of the vanilla dot. Okay? And this is a good example of how the peak of the choice of kernel that we do is important. Generally, you will observe, and the literature, as I was saying before, has reported better results for the radial basis function than for, you know, simpler kernels. Okay, let's stop here.